The heel effect is not a condition plaguing women around the world. Actually, the heel effect is a radiographic phenomenon that affects the intensity of the X-ray beam. Remember that the anode in general radiography is usually angled between 6 and 20 degrees. This is a good thing for two main reasons. First, the anode angle increases the surface area of the focal spot, which increases the ability of the anode to absorb heat. Additionally, the angle helps to decrease the effective focal spot size and therefore increases the spatial resolution of the radiograph. Unfortunately, the angled anode does have one negative consequence. The angle of the anode causes a variation of the beam's intensity across the X-ray field. Specifically, there are fewer X-ray photons on the anode side of the beam compared to the cathode side of the beam. So we would say that the cathode side has higher intensity and the anode side has the lower intensity. So why does this actually happen? X-ray photons are created throughout the anode and not just on the surface. So some of the photons get created deep in the anode and then they get absorbed within the anode heel. As a result, the X-ray beam has fewer photons on the anode side compared to the cathode side. And that's really the definition of the anode heel effect: decreased X-ray beam intensity on the anode side of the beam. Fortunately, the anode heel effect isn't all bad. In fact, if you understand the heel effect, you can actually use it to your advantage. For example, when performing an abdominal X-ray, the upper abdomen is less dense than the lower abdomen because the lower abdomen includes the very dense pelvic bone. If we purposefully place the anode side of the beam over the upper abdomen and the cathode side over the lower abdomen, this allows for more even exposure to the receptor. The high-intensity cathode portion of the beam is placed over the densest portion of the patient, and the low-intensity anode side of the beam is placed over the least dense portion of the patient. A few variables can actually change the extent of the anode heel effect. In other words, the change in beam intensity across the beam isn't always the same. Here's one example: decreasing the anode angle. In other words, making it steeper or smaller increases the anode heel effect. This is because more X-rays get absorbed in the anode and the beam intensity on the anode side decreases. In this example, you can actually see that happening. When we decrease the anode angle from 20 degrees to 6 degrees, an increased number of X-ray photons get absorbed in the anode angle, and so we have an increased difference in the intensity between the anode side and the cathode side of the X-ray beam. The relationship between anode angle and heel effect is inverse. That means as the anode angle decreases, the anode heel effect will increase. In other words, there will be an increased difference in the intensity across the X-ray beam. Changes in SID also affect the extent of the anode heel effect. Decreasing or shortening the SID increases the heel effect. Shortening the distance causes the receptor to get exposed to more of the low-intensity beam on the anode side and more of the high-intensity beam on the cathode side. There is an increased difference in intensity, which is the same as saying there is an increased anode heel effect. The relationship between SID and the heel effect is inverse. So as the SID decreases, the anode heel effect increases. The X-ray field size is one more factor that affects the severity of the anode heel effect. Increasing the field size increases the anode heel effect. Here's what happens. Using a large field exposes the receptor to more of the low-intensity beam on the anode side and more of the high-intensity beam on the cathode side. This, of course, results in an increased difference in intensity across the X-ray field, which is the same as an increased anode heel effect. The relationship between field size and heel effect is actually direct. As the field size increases, the anode heel effect also increases. So in summary, the anode heel effect is the change in beam intensity across the length of the X-ray field. Specifically, the anode side has fewer photons and the cathode side has more photons. You might say that the anode side is weaker and the cathode side is stronger. Also remember that the anode heel effect can be used to our advantage by placing the thinnest portion of the patient under the anode side of the beam and the thickest part of the patient under the cathode side. And finally, remember that 3 changes can increase the anode heel effect. First, decreased anode angle. Secondly, decreased SID. And finally, increased field size.